on some of the things that we've done previously, but it's not, we want to try to avoid using kinematics, basically, is what we want to do with this. Okay. So the biggest thing that you want to try to avoid is when you're solving problems right now with this chapter is don't use any of your kinematics equations. You want to try to think about it in terms of energy instead of like VF squared equals VI squared plus 2AD. That equation is off the table. Can't use it anywhere. There's a way to do it with energy instead. You could still use your force equations, your Newton's laws. They go back and forth between the two ideas, but really stick with the concepts of energy. When you go to take the AP exam, then you could do it either way. Okay, whichever way hits you. But right now, because we want to be focusing on the concepts of work and energy, I want you to use an energy approach to things. Okay, so let's get right into this chapter then on work and energy. So a force, remember, does work if its point of application moves through a distance and there is a component of that force which is parallel to the way it's moving, in parallel to its velocity somehow. Okay, so if I push something up, but this thing I'm pushing up is moving left or right, the force that I am exerting is not doing any work because it doesn't have a component parallel to the motion or parallel to the displacement. Why can't I get this to just move? Something isn't quite right here. Anyway, so when you do work on a system, when work is done, then energy moves between things. And remember, there's pretty much two types of energy we're going to be discussing in this course. They are kinetic energy and potential energy, where kinetic energy is associated with motion and potential energy is associated with some type of position or configuration of the system. And again, here's that note. Do not use concepts from kinematics. That's chapters 2 and 3. Don't use chapters 2 and 3. You can use Newton's laws, but you may not use any kinematics concepts here. Okay. So let's talk about work and kinetic energy specifically. So if we're dealing with motion in one dimension with a constant force, this is what we dealt with in Regents physics, this little piece of things. Work, remember, is the product of your force and your displacement. And if the force and the displacement are in different directions, you only want to use the component of the force, which is parallel to the displacement to determine the work that's being done. So in this diagram, you see how there is this force F at an angle of theta? The entire force of F is not doing work to move that box from the initial position on the left to the position on the right. Only the horizontal component of that force is going to do work because that's the component of the force parallel to the delta X, which means that what we would have to do is take F cosine of theta, which would give us the horizontal component of that force, and then multiply it by the displacement delta X. Now that's what you do when the force is a constant magnitude. Most forces in real life are not constant in magnitude. They vary over time, which means there's got to be another way to do this. And we'll get to that in just a minute. So work, remember, is W. W is not going to mean weight. It means work. We're going to measure it in joules, which we abbreviate with a capital J. Remember, the joule is a derived unit equivalent to a Newton meter or a kilogram times a meter squared per second squared. This is a scalar quantity. It has no direction, but work can be positive or negative. Now let's talk about what a positive work value means versus a negative work value. Positive doesn't mean you did work to the east or work going up. It doesn't include a direction. What it's telling you is that when you calculate a positive amount of work, that you have added energy to the object that work is being done on. You've added energy to it. If you get a negative amount of work, it's telling you that you decreased. That work is decreasing the energy of the object that the work was done on. Okay, so it's really talking about a change in energy. And that brings us to the work energy theorem, which we'll get to in a minute. So most of the time we know that there's more than one force acting on something. So this brings us to the idea of having a total amount of work being done, which is the amount of work done. Total work is the amount of work done by each individual force, and then you sum them together, acting on the object. And most of the time we're going to talk about a particle as the object that the work is being done on. A particle is kind of like what we did with a projectile, where we're dealing with something that's not rotating and it's perfectly rigid. So that way all components of the object have the same identical displacement. So the total work would just be the sum of the work done by each individual force that acts on the object. They all have identical displacements, and therefore the total work or the net work can be found by just using the net force that's acting on the object. So you would use the net force times the displacement to give you the work done. Kinetic energy refers to the energy of motion. In the AP course, we don't write it as KE. We just write it as K. So you'll see that on your reference table. It's just referring to a capital K for kinetic energy. That's what I want you to try to get used to now as well. Joules, again, is our unit. And the equation for calculating kinetic energy is pretty easy, 1/2 mv squared, where v just represents the speed of the object. It's not a velocity. That's because kinetic energy is a scalar. Kinetic energy can never be negative. It's only an unsigned amount. It's got a magnitude only. It can only be a positive type of value. Now, the work kinetic energy theorem comes from Newton's second law, which talks about the total work done on a particle equaling the change in kinetic energy. So the net work is always equal to the particle's change in kinetic energy. So if I were to take the net force and multiply by the displacement, that would give me the change in the kinetic energy. If I'm finding the work done by one force acting on an object, that does not give me the change in kinetic energy. Only the work done by the net force would give me the change in the kinetic energy. Now, this is where we start to get into the calculus piece of things. When you have a force that's variable, if I were meaning it changes over time and is therefore a function of the position of the object, the work that's done can be found by looking at the area under the force versus position graph. So that shaded area on that graph represents the work done by force F as it moves from x1 to x2. Now, we learned earlier in this course that when you're calculating an area between a line on a graph or a curve on a graph and the axis, it's like what calculus method? It's analogous to doing what in calculus? An integral, okay? So what this tells us is that when you have a variable force like this, you see how the force is not a line? So finding the area between that curve and the x-axis is going to be really hard to do. You can only get an approximate value if you're using an area, because you can't find areas with curves. So instead what we do is we look at an integral of force, but notice it's not with respect to time. You have to make sure when you're doing this integral that it's the integral of the force with respect to position. If you do the integral of force with respect to time, you're finding an impulse. And we know from Regents physics, an impulse is not the same thing as work, okay? It's a change in momentum, and it is. So when we do this integral, which is the integral from position 1 to position 2 of that variable force function with respect to position, that would give us the work that's being done by that individual force, not the network, by that individual force. So make sure it's with respect to position, which means the limits on the integral have to be positions. You're evaluating from one position to another position, not from one time to another time. That's probably the most common mistake I see with this, is that students want to use time in this because they're used to using time with all the other integrals we've done so far, right? Integral of acceleration to give you velocity, integral of velocity to give you displacement. Those are all with time. This one is with position, not with time. All right, this now brings us to some vector math because we're taking the product of a force and a displacement. Force is a vector. Displacement is a vector. What's really interesting about vectors is there's two ways to multiply them. One of them will give you a scalar result. One of them will give you a vector result. You learned about this over the summer, and right? You were introduced to this idea in that math video that I asked you to watch over the summer. So the first way we can multiply two vectors is in what we call a dot product method, where the dot, you're not going to put an X, that's something else called a cross product now. You actually put a dot between the two vectors. So in this case, for example, I have a force, and I can see an incremental displacement ds vector there. And the work that's done by that force F for that little tiny incremental displacement ds would be equal to the vector F times the vector ds. And again, I want the parallel component of F to ds, so I would use the cosine of theta in there. F cosine of theta. Notice that we're going from a bolded text to a non-bolded text. Remember, bolded text indicates it's a vector with a direction. Since we know work is a scalar, this type of multiplication is what we call a dot product or a scalar product, which means we have to figure out how to get rid of directions on things. It's not like multiplying 5 kilograms by 2 seconds. Those are both scalars to begin with. We're saying we're taking one thing which has a direction and multiplying it by another thing that has direction, and we want to get rid of the direction on our answer. The way we would do this is with this dot product type of math. So here we're showing you how to take the dot product of two vectors A and B. If I'm doing this thing called a dot product to give me a scalar result, then only the parallel components of those two vectors get multiplied. Vectors which are perpendicular do not produce an answer with a dot product type of math. That's something called a cross product, which we'll get to in future chapters. But here we have the general math of how you come up with the scalar product, the dot product. So we would read this as A dot B is equal to AB cosine theta. That's how you read that. And we actually have to see a dot between vector A and vector B to produce this answer. So in your textbook on table 6.1, which is, let's just see what page that's on so you can refer to this page. When you're doing problems with dot products from this point forward, you'll see that this is giving you all the ways that dot products work. This is on page 159 in your textbook, table 6.1. It shows you the different properties of dot products. So if you're doing a dot product with vector A and vector B, and these two vectors are exclusively perpendicular, since the angle between them is 90 degrees, we know the cosine of 90 degrees is 0. It means that the dot product result of A and B is 0. There isn't one. If you're doing it with two vectors which happen to be parallel, their entire magnitudes get multiplied. So it's just A times B. The magnitude of A times the magnitude of B, because the cosine of 0 degrees is 1. And you can get a dot product result of 0 if either vector A's magnitude is 0, or vector B's magnitude is 0, or if they're perpendicular to each other. So there are three ways to get a 0 result with a dot product. And then, of course, it shows you some other properties here, like the distributive property, commutative rule works still, and dot product of a vector with itself. Okay, so remember that we often use ij's and k's to refer to directions of vectors. So that would mean if I'm using these rectangular components ij and k, I dotted with itself has to be 1, because I has a magnitude of 1, and they're parallel to each other. So it's like 1 times 1. I dotted with j, however, I is to the right, j is up. Those are perpendicular, so that dot product result should be 0. So if I'm giving you two vectors A and B, and they're written in rectangular components, so vector A is ax in the I direction, plus ay in the j direction, plus az in the k direction, and I dot it with vector B, which is written this way with ijk, it means the only things that I really have to worry about distributing are the components which are in the same direction, meaning I just have to take AX and multiply it by BX. I don't have to worry about distributing the AX in the I direction with the BY and the J. Why is that? Why don't I have to worry about that? Because I dotted with J is 0. It's going to drop out. Likewise, distributing this X component with B's Z component, that's going to drop out as well because I to the right and K coming out are perpendicular. They drop out. So what I end up getting is just a scalar result of multiplying the magnitude of the X component times the X component. So multiplying the X components together, adding it to the product of the Y components, and then adding it to the Z components. And of course, why am I adding it? Because you see the addition here in those two terms. Okay, now this is showing you how to use the derivative with a dot product, because you are going to be doing derivatives with dot products. We'll be doing that in just a minute, because the derivative of work with respect to time is power. And work is a dot product of force and displacement. So I could just do the derivative of force times displacement, that dot product over time. And that would be showing you something like this. Notice this shows you how that derivative gets distributed to both terms. It's called the chain rule, I believe. So using dot product notation, we can see that that means the derivative of work, which is the work is F cosine of theta times the derivative of a displacement is therefore F ds. So that's vector F and vector ds. Now, if I want to get rid of this little incremental piece of work that's done, I have to take the integral on the right side, which gives me the integral of the force with respect to the displacement vector from position 1 to position 2. So here we're just using the letter S instead of X, because it's not always along the x-axis. It can be along any axis as long as they're parallel to each other. All right, so let's now talk about power. We learned in Regents physics that power is the rate at which work is done or energy gets transferred. So that means, still using a capital P for power, measured still in watts. A watt, remember, is a joule per second, which means that if I'm doing a rate, it means I'm taking something and dividing by time. In broader terms, that means we take a derivative when I have a function with respect to time. So the derivative of a work function with respect to time would be the dot product of the force and the velocity vector. Again, it's a dot product because we get a scalar result for power. All right, let's now talk about, well, this is the same thing. I'm skipping this. Remember, the total work done is the change in kinetic energy. All right, let's talk about potential energy then. Potential energy refers to energy that's stored in a system. And the symbol we use for this now is a capital U. We're not going to use PE. Capital U. Okay? Capital U stands for potential energy. And we'll add subscripts to it. UG would mean gravitational potential energy. US, elastic potential energy. Okay? So this is in joules still. Our two kinds, UG and US. This is showing you gravitational potential energy. That's showing you some elastic potential energy. And this now brings us to a big discussion about types of forces. Forces can be classified as either conservative or non-conservative. We touched on this with you in Regents physics, but we did not go into detail. This course requires us to go into detail about these types of forces. So that's a big difference. And you need to understand what is meant by a conservative force versus what is meant by a non-conservative force, especially when we start to talk about potential energy. A force is conservative if the total work it does, meaning that force, the work done by that force, on a particle ends up being 0 when the particle moves around a closed path from its starting point around and back to its starting point. So if the work done by this force is 0 on this closed path, that force is said to be conservative, which means that the work done by a conservative force on a particle would be independent of the path the particle takes as it moves from one point to another. So examples of forces which are conservative, where we really only need to consider the starting position and the end position of the particle, are forces like gravity and springs, as long as the spring is ideal, meaning there's no thermal loss in the spring. Real springs heat up as they stretch and compress. So a real spring would not classify as a conservative force. But if it's an ideal spring with no thermal energy loss, then you could consider a spring force to be a conservative type of force, because the amount of work done by these is always the same when you return them back to their initial position without any thermal energy loss. The best example I can give you of a force which is therefore non-conservative, where the work is different depending on the path you take, the longer the path, the more work gets done, would be friction, right? Because the more distance you have with a frictional force, the more heat you're going to create. Okay, so let's now talk about potential energy. Potential energy can be discussed in terms of these forces and displacements. Notice that equation, the first one there, 620A, looks a lot like the work equation we saw a minute ago. Integral of force with respect to position, from position 1 to position 2. But notice there's something in front of the integral here, a negative sign, okay? The negative sign is telling you that the change in your potential energy is negative work. The change in your potential energy is the negative work that's done. So that means, I'm showing you an equation there for du, incremental potential energy. I'm going to move that around for force. So it means that if I were to take this equation and solve it for the force vector, it would be negative du ds. Now remember, s is just a general position term. It could be x, it could be y, it could be whatever direction this thing is moving in. So it's the negative derivative of potential energy with respect to position. Where before, we also said that work was the derivative of the work done with respect to position. So these are opposites of each other. All right, so gravitational potential energy, this looks a lot like the equation we saw last year, mgh, or mg delta h. But we're just including a y instead of an h. We're using a vertical position. We're also including in some initial potential energy, u0, which would be the value of some potential energy when we're at the ground level. Usually we say that u0 is 0. We're going to assume the potential energy is 0 at the ground level. So choose u to be 0 at any convenient reference point, usually the ground, or the lowest point in the problem. Maybe it doesn't get all the way to the ground, but we stop looking at things at this height, say the potential energy is 0 here. That's fine. Remember that when objects attract, the farther apart, the more potential energy they're going to have. Think of it like this piece of chalk in the earth. Piece of chalk has a certain amount of potential energy right here, gravitational potential energy. If I move it further away from the earth, what happens to its potential energy? It goes up, right? Because I've increased its height. So that should help you understand that last bullet item. The further apart things are, the more potential energy they will have with each other. Elastic potential energy. First thing we have to talk about are ideal springs, which always return back to their original configuration after you've stretched them or compressed them. Of course, we have Hooke's law, which we talked about in a previous chapter, that if the spring is ideal, it would obey Hooke's law, where Fs is minus Kx, minus just being opposite in direction. When a spring gets stretched or compressed, and it's ideal, the elastic energy in that spring would be 1/2 Kx squared. We learned that last year. We said PES was 1/2 Kx squared. Well, we don't use PE, we use U now. So there it is. US is 1/2 Kx squared if the spring is ideal. If it's not, you can't do that. And again, X being 0 is the equilibrium position of the spring when it's neither stretched nor compressed. It's at its natural length. If I'm dealing with a general conservative force, could be gravity or a spring force, the force is the negative derivative of the potential energy with respect to position. I have that up there on the board. This is more specifically in the x direction. And a particle would be in equilibrium if the net force is 0. That's Newton's first law. If the net force on something is 0, it's in equilibrium, which means that I could plug in a 0 value for the force there into that potential energy derivative equation if you're in equilibrium, which brings us to discussing 3 different types of equilibrium that you might have. Notice what I'm showing you is a graph of potential energy with respect to position. If your graph of potential energy with respect to position is concave up, that graph is concave up, right? It means you're in what's called a stable type of equilibrium. What does it mean if you're in stable equilibrium? It means if you push something a little bit away from its equilibrium position, it goes right back to its normal position. So take a spring, stretch it just a little bit, let it go. It goes right back to its normal length. That would be a stable type of equilibrium you have. Okay? If you're in a stable equilibrium, you get a graph of potential energy versus position, which is concave up, like what you see there. If you get a potential energy versus position graph, which is concave down, like this one is, you're in what's known as an unstable type of equilibrium. How would you know if an object is an unstable type of equilibrium? Unstable equilibrium means you pull something away from its equilibrium a little bit, and it accelerates even further away from the equilibrium. I'm going to think of like a car. I take a car and I tilt it away from its equilibrium, and it continues to fall all the way over, like it rolls over. That would be an unstable type of equilibrium. That happens when your center of gravity is too high. Okay, that's why there's some rollover issues associated with higher centers of gravities on vehicles. So that would be an unstable type of equilibrium, which would produce a graph like that. If you're in a type of equilibrium known as a neutral type of equilibrium, you get a graph that's neither concave up nor concave down. It's kind of like flat. You're not seeing a curve up or a curve down. This is neutral equilibrium, which means if I pull something away from its equilibrium, it just kind of stays there. It doesn't accelerate further away. It doesn't accelerate back. It just kind of stays where we're at and in another equilibrium position. So on a potential energy curve, if you're at a minimum on your potential energy curve, if you're at a minimum on your potential energy curve, that would mean that the force acting there is 0 and the system is in a stable type of equilibrium. That's when the graph ends up being concave up. Think about it. When you're at the minimum, that's when the graph is concave up. So you're in stable equilibrium there. If you're at a max, then the force is 0. Tangent line derivative would be 0 there. And the system is now in an unstable equilibrium position because now the graph would have to be concave down at that point. And a conservative force is always going to tend to accelerate a particle toward a position of lower potential energy. Think about it, gravity. Gravity is going to act on this pen. It moved it towards less potential energy. It's a conservative force. Things want to go towards lower potential energies. Let me go back to the first 2 bullets here. Determining mins and maxes. In calculus, you'll be doing things like taking second derivatives of functions and then evaluating them at points, looking for positive or negative, whether things are positive or negative. If you get a positive result, you're at a max. If you get a negative result, you're at a 0 or a min. That's what you do here to determine whether you're at a max or a min on a graph. And if you get a 0, that would mean neutral equilibrium. Okay, so just remember, second derivatives help you evaluate concavity. Second derivatives of functions help you evaluate concavity. So if I give you the potential energy function, take the second derivative, plug in the position, and if you get a positive value, you're at a max. If you get a negative value, you're at a min. If you get 0, it's neutral equilibrium. Okay, second derivatives. I remember doing that when I was in calculus, having to find points of inflection. Where do these graphs? That's what you're doing here for these. All right, that's it for this chapter. So we have about, it's 8:48, periods over at 57. All right, so if you want to start working on the assignments that are due Monday and Tuesday next week. So assignment 32 is due Monday. Is it connecting? Yes, it is. And if I check, let's just double check what assignment 32 is. I believe it's the reading guide, but it may not be. Forget it. I'm not even going to look here. I'll look in my plan book. Actually, let me get down to, do you guys have this all topics button in your student version of Classroom? You do? Okay, so you can go right to chapter 6 and 7 without having to drill down. You'll see that you get the PowerPoint is there now for you. But here's assignment 32. Yep, it's the reading guide. The reading guide. So the reading guide is due Monday, and then there are chapter problems due Tuesday, so you can start working on those as well if you'd like. But you also have your coffee filter lab report, which is due Tuesday, to be working on getting that done. Okay, so I'll give you the rest of the time to work. I'm still waiting for a student to take this chapter 6-7 test. I'm just thinking we'll do corrections, not 6-7. 4-5, the 4-5 test. I'm thinking we'll just do corrections on that after Thanksgiving. Okay, and we'll talk about the show work section after Thanksgiving as well, most likely.